So, stat edit. Hey, don't be mean. So you should have, oh man, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17?
Yep.
What? Okay. And then 59, 30, 60, 06.
What?
Yes, there is a regular stats.
Really?
Yeah. Yes, there is.
Okay.
This might not be till second semester. I think Schilling's going to teach it and Albury.
Are we only do one?
It's a semester class. The discrete math class is the other semester of it. So Albury teaches discrete one semester and then stats the other semester. But it's not the same students. Okay. So then we can go stat, calc, exponential regression. All right. Whoa, that's weird. That's interesting. 11,448. Yeah, that can't be right. What did I do?
The R is negative.
Yeah.
What in the world just happened? Did I take my numbers all in right? No, I most definitely did not. There's my problem. Okay. All right, let's try that again. Stats, calc, exponential regression, L1, L2. There we go. Okay. So here's what we get. We get the equation. Oh, look, we still have from our notes last week. Why are those different? Oh, yeah, you're right. You changed the starting value. Good. Okay. So we get something like 5,400 times 1.0119 to the x power. What if I wanted to write that as an equation using a base e exponential instead of a base 1.0119? How do I find out how to write that as 5,400 times e raised to the something x? How can I figure out?
Do e to the number and then times e to the x.
What I actually want, I want to know what the natural log of that number is. Won't the natural log of that number, that 1.0119 number, did you get angry with it? Did ripping your paper make you cry, is the question. No, good. Okay. So I want to know what's the natural log of that 1.0119 number. I can actually go natural log, and that number is stored in my calculator. If I go vars, statistics, and then go over to EQ, guys, and then select B. So I can actually say, use a lot more of the stored decimals. So apparently if I do 5,400 times E raised to the 0.01185, that right there is an equation that models this population growth, where a time of 0 corresponds to 1990. And so then, so on and so on. Because if you ever want to take a number, any number, pick a number. If you want to take the number 4, and you want to figure out how to rewrite it, and somebody pick another number.
11.
How can I write 4 as a power of 6? 6 raised to what power gives me 4? All I got to do is know what is the log base 6 of 4. And whatever that number is, I can write 6 to that power, and I'll get the number 4. So if I want to take the number 1.0119, but I want to write it as a power of e, I take the natural log of 1.0119, and that's the number that I can raise e to get 1.0119. Yeah.
Why do we have to do that?
Because often we will take, usually when you have a population growth of some sort, you often want to rewrite it as an exponential to e. Okay? So if we move on in our notes, hey, look what the book came up with. 5400 e to the 0.011852. Is that what we got?
Yeah.
How about that? Pretty sweet. Okay? So that is that's how the books came up with this function to model this population growth. They did the linear regression, or they did the exponential regression, but then manipulated it to write it as a power of e. And of course, they are saying the time t equals 8 represents 1998. Compare the values in this model with the actual values in the table. So if I were to plug 9 in and then check 1999, the numbers should be pretty similar. How can I figure out when the population will reach 6.8 billion? So I say 5,400 e to the 0.011852t equals what? Good. So that's going to be 6,800. Because remember, this is modeling the population in millions. So 6.8 billion will be 6,800 million. So now, how do you solve this equation? First, we divide. So we have 6,800 divided by 5,400. And then do what? Natural log, so 0.011856 equals the natural log of 6,800 over 5,400. And then what's the last step? I keep forgetting my t. Divide. So t equals the natural log of 6,800 divided by 5,400, all divided by 0.011856. Or not 6, that's a t. Oh, that was my t. My t's are looking like 6s. Oh my gosh. T. And no 6. There we go. So we can type that in. Natural log 6,800 divided by 5,400 divided by natural log b. So you get 19.45. 19.45 is what year? The year 2009.
Why did you divide by natural log?
Well, natural log b was what this number is. So I just had more decimals by doing it that way. I could have typed it in, but I'm lazy. So does that make sense? So if you want to solve for when an exponential growth function hits a certain point, make an equation, and then use logarithms to solve it. Make sense? Okay. The other types of word problems. So the big focus here is using logarithms and exponentials to solve word problems. Okay? So in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300, and we are told that they are growing exponentially. What is the equation? Well, they want us to know how many flies are there after 5 days, but we're going to create the actual equation telling us how many flies there are, and then use that equation to calculate how many after 5 days. The general exponential equation is an equation that looks like this, a times b to the x. Agreed? Right? Where A is how many fruit flies there are at the beginning of this experiment. Do we know how many flies there are at the beginning of the experiment? No, I'm guessing it's reasonable to assume there are less than 100, but I don't know for sure. What I do know is if I plug 2 in for x, so I am letting the x variable represent number of days. So if I plug 2 in for x, y is going to equal what? 100. I also know that if I plug 4 in for x, y is going to equal what? So what I have is a two-variable, two-equation system. So what I would recommend, actually, is substitution method. Solve one of the equations for A, and then plug in, and then you'll have what is a, in reality, it's a simple algebraic equation, but it's a little bit different, so some people might struggle with it. Or, I'm going to use a little rule that says, if I divide one side of the equation by something, I have to do what? Divide the other by the same thing. So I'm going to take this equation here, and I'm going to divide the left side, a times b to the fourth. I'm going to divide it by a times b to the second, which means I have to divide the right side by what? The same thing, which is 100. Because isn't a times b to the second and 100 equal to each other? Yes. Right? That's what that second equation is telling me. This is essentially the elimination method. It's just with linear equations, you do what with the equations to eliminate a variable? You add or subtract them, right? When you add the equations together, hopefully your x and your negative x cancels, right? Well, here, these aren't linear equations. But by dividing them, what variable is going to eliminate? A. What's a times b to the fourth divided by a times b to the second? It's just b squared, and 300 divided by 100 is 3. So we square root both sides and get plus or minus radical 3. But because b is the base of the exponential, we've already talked about how the base can't be negative, right? So b is positive radical 3. If we plug that back in, you're going to get 3a equals 100, so a is 100 thirds. So your equation is 100 thirds, what's that?
Oh, wait.
Yeah. So there's your equation. 100 thirds, which is roughly 33, that's how many fruit flies there are at the beginning of this experiment. So we start with 33 fruit flies. After 2 days, there's 100. After 4 days, there's 300. And then just plug 5 in to see how many there are after 5 days. So 100 thirds times radical 3 to the fifth. And so if we plug that in, oops. We get 520 fruit flies. What's that? $519.6 when rounded becomes 520. Or not. If I've got more than half a fruit fly, I'm counting that as a whole fruit fly. Yeah, 0.6 of a fruit fly. It's not fair to 6/10 of a fruit Let's look at it this way. So, I didn't hear you said.
I said, so you're saying if you don't have an arm, you shouldn't count as a person. Bam.
Bam.
What?
Okay. That was good. Listen. So, according to the calculation, there should be 519.6 fruit flies, right? But clearly you can't have 0.6 of a fruit fly. So let's look in terms of probability. What is more likely to happen on that fifth day? Having 520 or having 519? Because the calculation is saying you should have 519.6. So clearly that can't happen. So is it more likely we'll have 520 or is it more likely we'll have 519? I think probability-wise, because our calculation came to above 519.5, it is more likely that we will have 520. We're not going to have 0.6 of a fruit fly. So probability-wise, you should have about 520. Okay. But did that make sense? How we created the model. Now here's the interesting thing. Did you ever know this? If you go stat calc, listen, if I plug in 2 and 4, and then plug in 100 and 300, and I then do an exponential regression. 33.3 repeating, that's 100 thirds, correct? And what do you suppose that number 1.732 is? That's the square root of 3. Look at your R value. What does that mean? That means not only is this a best fit, this equation actually perfectly goes through those 2 points. Which, think about it. If you're only given 2 points, shouldn't you get the actual equation of the exponential that goes through them? How many of you, when you're in Algebra 2 and your teacher asked you, find the equation of a line that goes through these 2 points? Actually, just plug those 2 points in your calculator and did a linear regression. Nobody? You should have. It's an easy way of doing those problems.
We didn't have that
You did when you took it last year. Those problems are on the first exam. Saves you a lot of effort. It's a great way to check your answer at least, right? If you're only given 2 points, do a linear regression. Is there only a line that comes close to going through 2 points? No, there's one single unique line that will go through those 2 points. You will get a correlation coefficient of exactly 1, and it will tell you the actual equation. Isn't that smart? I know how to cheat. Okay. Here's my other, these are my favorite, I love word problems like this. Carbon-14 dating. Do you know how carbon-14 dating works? There's a little paragraph that summarizes it. You can read that, or I will go ahead and explain it to you. So every living thing has carbon in it, right? It's the definition of organic. Okay, it has carbon. But there are lots of different types of carbon. There's carbon-14, which was the 14 means what? That means right. So it's not the number of protons per carbon is 6 no matter what, right? No matter what, carbon has 6 protons. So carbon-14 then has how many neutrons? 8. So carbon-14 is a carbon atom that has 8 neutrons, so 2 extra neutrons above. I don't know. But carbon-12 is your regular type of carbon that has 6 protons, 6 neutrons. Carbon-14 is radioactive. Those 2 extra neutrons make it radioactive, meaning what? It's decaying away. Okay? And whenever a substance is radioactive, it decays exponentially. Okay? Specifically, carbon-14 decays in such a way that every 5,715 years, you will have exactly half of what you started with. So if I were to take a chunk of 10 pounds of carbon-14, and we just watch it, after 5,715 years, we will have exactly 5 pounds. After another 5,715 years, we will have exactly 2.5 pounds. After another 5,715 years, we will have 1.25 and so on. Will you ever get to the point where you have 0 pounds? In theory, no. Right? Because it just keeps cutting in half. In practice, eventually you'll have 2 atoms. And then after 5,715 years, you'll have 1. And then what happens after 5,715 more years? You have half of an atom. All of a sudden it turns into, I don't know, whatever 3 is. Yeah, it would explode fission. That's bad. So I don't really know how it technically works once you get down, but I don't think, how long would it take? Because you're talking moles then. How long would it take to get down to 2 atoms if you started with like a gram? It would take an amount of time that we cannot comprehend yet. Stuff will not exist that long. Okay, so that's how it works. Now, It just so happens that in living beings, there is always this constant ratio of carbon-14 to carbon-12. Okay, and that ratio is 1 to 1 trillion. So for every trillion atoms of carbon-12, there will be one single atom of carbon-14. There's not a lot of carbon-14 in us, luckily. We're not terribly radioactive. Just a little. All of us. Okay? So what you end up with is this. When I die, I have exactly a ratio of 1 to 1 trillion carbon-14 to carbon-12. And that will be multiplied by 1/2 after how many years? 5,715. So I take that 1/2 and I raise it to the t over 5,715. So basically, when I plug 0 in for t, that's how much I have initially. When I plug what in for t, I'll have exactly half. What do you have to plug in for t to represent the first half-life? You plug in 5,715. If you plug 5,715 in for t, what is your exponent? 1. So you multiply by 1/2. You have exactly half of your ratio. 1 to 2 trillion. If I plug whatever double 5,715 is, if I plug 14,030, is that right? No. Is it? 11,430? Sure. Yes, that is correct. If I plug 11,430 in for t, you'll have exactly 1/4 of your initial ratio. But look at how they wrote the equation. They wrote it using E. Weird. Figure out why. Homework's the same as last Thursday. So, none, technically.